Yes, wonderful to be here. It's been, I've really enjoyed the talks, enjoyed the conversations so far. Please feel free to interrupt me. So yes, we are in this realm where AI is everywhere. We have AI for agriculture, we have AI for education, AI for law, AI for social decision making. These are real institutes. AI for physics, AI for cooking, and so we have AI for brains. And so I'm the associate director of ARNI, the Institute for Artificial and Natural Intelligence. It's based at Columbia. It's a cool group of people, but it's about neuro AI. And now is a really good time for neuro AI because of this confluence of a few different things. One of them is just massive data. We just published with a large consortium, the Microns Consortium, a functional connectome of the visual cortex of mouse. 1 cubic millimeter, where all of the detailed structures, structural connectivities are known at the nanoscale, and also how those neurons respond is measured. So this is a historic data set, and now it's ready for mining. Go ahead, mine it. We also have massive fMRI imaging sets. It's just a lot of data, a lot of new techniques. And then we have massive compute, which is allowing us to build things like big foundation models and using these things dynamically to have closed loop brain interfaces. In order to do this, we really need all of this is the time for neuro AI. It's a good time to be here. This is an example of a functional connectome, a small part of it. I guess zoom animations are a little bit tricky, but the flashing ones are when the neurons are responding. And you can see from the graph which ones are connected to which other ones in a moment. There we go. Slow animations. Okay. Should I hold up my laptop? It's being recorded. Okay. So the goals of neuro AI are to go in these two directions that we've been talking about, not just to use AI tools to understand the brain better, which is a fabulous thing, but also to get information from the brain that can help us build better AI tools. So how do we do that? Today, I'm going to talk about really 2 or 3 things. First, I'm going to spend some time talking about principles of generalization, because that's really what we're after. We're after not something that, a system that could be fit to data, but to something that can go beyond the data. So what are the things that can contribute to that doing well, and how can we understand something new from the brain? And I'll tell you a little more detail about one particular project within that domain, which is focusing on 3-way interactions, which I think connects a lot of ideas that we've already heard about today. And then I'll talk a little bit about another major thing that brains do really well, which is efficiency. So we'll talk about principles of constrained control, which we're thinking of as frugal inference when you have to act. And then we'll have a little bit of a discussion at the end. So let's start with principles of generalization. The problem is that here we're talking about neural networks. Neural networks can compute anything. They can approximate anything. And this has been known for decades, just one hidden layer. But the problem is that even though you can fit any function, it doesn't generalize. And it doesn't say anything about how hard it is to find such a solution, such an approximation, or how much resources you would need. And so, but the key is really, how does it generalize to new things? You don't want to just have a lookup table that crashes every time you go outside of your pre-existing data. So what is it that leads intelligence to better performance here? Well, in machine intelligence, what are we doing? We're going big, right? Big data, big compute, all of that's being big money. It's doing bigly well. But in neuro AI, what do brains do? Brains go small. Brains do much more with much less. We have much less data. I personally have not read the entire internet, but I can read. And I burn about 20 watts in my brain, compared to 10,000 watts for ChatGPT inference algorithms. So all of those things that lead our brains to be really good and to generalize better contribute to what we call the inductive bias, which Chris mentioned earlier. Inductive bias just means learning bias, and it's basically the things that you assume that lead you to generalize as a consequence of your assumptions. So in other words, what do you learn from a given data set? If I give you the data set, or maybe I give you a world to interact with, what do two different systems learn from that data set? They'll learn different things if they have different inductive biases. So they will generalize to new things in that world differently. So maybe one system will favor finding high frequency patterns and another system will favor finding low frequency patterns. Let me give you an example of an inductive bias, an embodied one. So for all of these different languages, Navajo, Mandarin, Xhosa, Quechua, Polish, the word for mother is like basically the same, ama. Right? Why is that? Well, it's pretty natural. It's the sound, the simplest sound that we can make when we open and close our mouths as little babies. Before we have much control, we can go and then that gets anchored, grounded to one of the most important quantities, attributes in a baby's life, their primary caregiver. So this is not inherited. This is just very natural as a natural thing to learn given our body. So the way that I like to think about contributions to inductive biases are in terms of this grid, big and small things at the circuit and learning level. And so I'm just going to tell you about some of the elements of this box. Let's start with microcircuits. So small things involving the way that neurons respond. So at the single neuron level, in machine learning, we use different nonlinear activation functions, right? We might have a ReLU or some ALU or a sigmoid, maybe something slightly more complicated. Real neurons are much more complicated. They might even be considered little neural networks unto themselves. Then when you combine them, we usually in machine learning take sums and maxes and maybe products. But of course, in the brain, you have much more intricate circuitry. And we're left with questions of how much of that circuitry is biological housekeeping versus having a computational function. And I think that this is a really critical question for us to disambiguate. Common microcircuits that you see in both machines and in brains involve these three attributes. You have sparsity, normalization, and attention. And it's arguable how much of these things are exactly the same in these different cases, but sparsity is basically rarity, right? And we have sparse autoencoders, which were mentioned. If you have neurons firing, they fire rarely, so it gives you a sparse representation, few things. And imposing sparsity as a goal leads to better computations in many cases. It makes it more interpretable. It makes it more aligned with the causal structure of the world. There's good reasons for that. So if you look at sparse coding, you find sparse coding of natural image patches. You end up with visual features that look very much like what you see in the primary visual cortex of primates, these edge detectors. If you do non-negative matrix factorization, which means you have to represent an image in terms of a sum of non-negative components, you're going to be sparse because you better not add anything if you're not really sure about it, because you cannot subtract it out. So again, you get sparsity out of this, and it leads to good representations. In fact, kind of interpretable ones of eyes and eyebrows and separable features. For another canonical operation, microcircuit level, we have normalization. In fact, I would argue that normalization is the canonical example of a canonical operation, right? If anybody says, what's a canonical circuit? They're like, oh, normalization. But in machine learning, we have lots of different kinds of normalization, batch norm, layer norm, div norm. In biology, things seem to be related to div norm, but you can make arguments that all of these things are manifesting in some way in biology. And they do things like explain responses of visual neurons to natural images, particularly when you have flexible divisive normalization that depends exactly on the configuration. You can change dynamically what should be normalized. And so the dots here, the vertical axis is how much you're modulated by the context of an image. You present an image patch and its context. How much does the response change with the context around it? And the flexible normalization model does a pretty decent job of fitting the data. This is from Carnegie. So normalization, a very common operation. Another one that's really important these days and very popular is attention, because this is one of the primary operations that shows up in transformers, which is the engine that powers ChatGPT. And this is the function for self-attention, where X is the input, and then you apply this kind of complicated looking function, and you end up with a changed representation. And so we can actually understand this function in terms of products, sparsity, and normalization. These are the three ingredients that show up here. So the key and the query product, which again we've heard earlier today, are really the product of different projections of your representation. So you take your representation X, you project it in two different dimensions by WQ and WK, and then you compare all of those representations to each other. You get a matrix, and those matrices, all the elements, are then treated basically as a probability. You sparsify them, so you figure out which ones of those overlaps, the similarities between keys and queries, are highest. Those are the ones that you're supposed to attend to. And so the exponential is going to magnify those numbers and compress all the rest of them. And then you normalize it to make it a probability distribution. And this whole thing becomes your attention weight on another projection of your input. So again, a product. It's just product, sparsity, and normalization, these canonical circuits. And you just do that again and again, these microcircuits. So I want to spend a little bit of time now talking about how that kind of thing can emerge naturally in biology. So my argument here is that gating nonlinearities like this product emerge generically if given the chance. So here's the framing. We have some feed-forward network, and at every point we have an activation function, which takes a weighted sum of your different inputs, passes it through a nonlinearity, and then that becomes the output of that neuron. And then you can give that to another set of neurons, which takes another weighted sum. And here, all these purple triangles, which are the activation functions, are going to be treated the same. Usually it's a ReLU. Sometimes it's something a little more sophisticated. But now let's consider what biology does. Okay, so I'm going to parameterize that activation function. It's just a function, right? We can parameterize it however we want, but here we're going to parameterize it by another little neural network in the inside there. Okay, it's just a mathematical convenience to parameterize the function. So we have one input to that network, some way of transforming that input into an output. And it's going to be shared for all the activation functions in this network. Real neurons are more structured, as we already talked about. And one very prominent thing that people have described is that they have two types of inputs. They have basal and apical dendrites. So we're not going to use any more of the biology than this, but those two inputs end up having different effects on neurons. So what happens if we allow artificial neural networks to have two different kinds of inputs? So now that little shared network is going to have two different projections of their inputs. So you're going to take all of the inputs from before, project it in two different ways, and then transform that by some parameterized activation function into the output. So it's just a slightly more complicated nonlinear function. We can consider that a single neuron microcircuit. So now we're going to train this thing and figure out what emerges when you give it the possibility of having a function, an activation that depends on more than one input at a time. So instead of having a ReLU here, which is going to be that little box, we have this inner network, which is a two-layer, multi-layer perceptron. And then we're going to put that activation function in a variety of architectures. It might be in an MLP, it might be as the nonlinearity in a convolutional network, et cetera. Okay. Then to train it, we're going to use three different phases. Phase one, we're going to initialize that inner function to some nonlinear, some very complicated arbitrary nonlinearity, because we don't want it to be smooth in any particular way. We just want to give it a kind of baseline. Okay, so that's just the initialization. Then in the second phase, we're going to train everything. So we train all the weights and biases of the outer network, like the regular network that you think of. And at the same time, we're going to train that inner network to parameterize the activation function. And then finally, in session 3, we're going to freeze the activation function. We have now done evolution. We've found our microcircuit, and we're going to use it. And now let's put it in a new network. We're going to train it on new tasks, or the same, maybe the same kind of tasks, and only train the outer weights, leaving the activation intact. Okay, and then we'll see how well it performs. So here's what happens. So we start with, this is the distribution of inputs projected into these 2 different dimensions, right? We have 2 dimensions of the inputs, and we normalize it so that there's some distribution here. And we have the pre-trained nonlinearity. And then after all this learning, that second phase of learning, we end up with these 2-dimensional activation functions, where red is a positive output and blue is a negative output. And in the right-hand column, you can see the performance as a function of what kind of activation function you're using. So we have the trainable ones in green and red, and we have the ReLU, the fixed ReLU, in blue. And so you can see the 2 phases. There's the first phase up to 200 here, where you're training both. And then the second phase is, okay, fix your activation, and let's see what happens. And let's zoom in on one of these, and we'll see what happens. So we're training both here, then we're training only the outer network. And what you see is that the red, which has the 2-argument nonlinearity, is doing a little bit better than the 1-argument nonlinearity in green, and better, still not a huge amount, but on these simple kind of tasks, we're already pretty close to saturating performance, better than the ReLU. So it's at least promising that you're not messing something up dramatically. And then what we can do is we can take a look and see what is it that you're learning in this activation function. So here we have a few different 2 different architectures, a multi-layer perceptron and a convolutional network, and a few different and 2 different tasks, either MNIST or CFAR. So both simple classification tasks. And one thing that you see is that there's a certain set of patterns that repeat multiple times. Each one of these is a different run of the same experiment. And what I notice is that there's a lot of these kind of X-shaped things, right? Where you have red and 2 red lobes and 2 blue lobes kind of opposite each other. And then sometimes you get this kind of ring shape here where you have a positive activation and then a negative activation. So these are really equivalent to soft AND-like or soft XOR-like. Right? And XOR is essentially a product. If you multiply X times Y, then if they're both positive or both negative, then you get a positive response. Or if one of them's positive and the other is negative, you get a negative response. It's exactly this X quality here. And there's a degeneracy. You can rotate it any way you like, because the weights in the outer network are going to absorb that. That's going to be completely equivalent. So the architecture seems to favor, if you have a convolutional network, more of these XOR type problems, these XOR type activation functions. And if you have an MLP, for some reason that I don't really understand, it favors these more AND-like functions. But one thing that I find really interesting here is that, first of all, you're finding something which is not just essentially a 1-dimensional activation function that's translated across that second dimension. And that's really important because we've controlled for the number of parameters. So if you have just made something linear, like equivalent as like invariant to that second dimension, you've effectively lost half your parameters. So you need to have a nonlinear interaction in order to take advantage of your functions. And the second is that you have these fairly smooth functions, which shows up pretty automatically from natural regularity assumptions. If you have a wide neural network, it tends to be smooth, even if like all the elements are parameterized by cusps. And the reason is sort of the central limit theorem. This is well understood. So the smoothest thing that you can get, which is still nonlinear, is a quadratic, right? It goes beyond just something that's x. And now what kind of 2-dimensional quadratics do you have? Well, you have like x squared plus y squared, and you have x squared minus y squared, or x times y. They're essentially equivalent. So this is very natural. that this appears, but you have to give the activation functions the opportunity to have more than one input to compare. And it seems that this gives you at least a tiny edge on some simple tasks. And I think it's interesting to look at what happens if you put this on a bigger scale. This product type of operation is not just used in attention, but it's used also in vision. And one of the most prominent models of visual perception of motion actually uses this product. And it can explain this pretty fun illusion here, this optical illusion. Have you guys seen this one before? I think this is pretty powerful myself. You see these flashing cubes, and they're not moving, right? They're basically standing still, but it gives you the very strong feeling that they're moving. This is something called the reverse phi illusion that somebody cleverly put into different configurations so that essentially by flashing on and off, a rightward movement with positive color is also giving you, if you follow it by a leftward movement with a reversing color, that gives you this illusion of consistent motion direction. Why? Well, there's a microcircuit there in your visual system which multiplies the two signals with a slight time delay. And that multiplication has this strange illusory effect that you don't see in nature. But if you have a mad scientist around who can concoct some cool illusions, then you can see that revealed. More generally, I think that this idea of a multiplicative interaction can become a really powerful motif, much the way that a transistor suddenly elevates you from having a very low expressive power of your circuit to having all the logic that we see in modern computers, digital computers. So I call this three-way motif, which is essentially the product operation here, a statistical transistor. So how many of you are familiar with probabilistic graphical models? Okay, a subset of you. If you don't know about probabilistic graphical models, check them out. They're really cool. It's a great way of capturing structure in data. And it's structure through a graph. Basically, if you put an edge in your graph, you have a statistical dependency, a conditional dependency. So here we have X, Y, and Z that are all connected to each other through a three-way interaction. And if you plot the joint distribution implied by this, it gives you this kind of pattern. And I've taken some slices through it to illustrate what happens as you change one of the variables, like here's Z. So if Z is low, then X and Y are anti-correlated or negatively interacting here. But if Z goes positive, now all of a sudden that contour rotates and now they're positively interacting. And if Z is in the middle, there's a cross section in the middle here, which is a circle. So what this means is that you can, with one variable, change the interactions between other variables. That gives you the flexibility of routing and gating and all of these kinds of things. It shows up in probabilistic inference in some very natural contexts, like you're trying to tell something, the color of something, when you have the surface reflectance times the illuminant coming in. You can make a whole bunch of different graphs out of this simple motif. You see this three-way motif appearing in multiple ways, and it can actually explain neural tuning with respect to different contexts, like that divisive normalization I showed you before. And this is a visualization that I just cooked up in the last hour. I was trying to make it dynamic, but didn't get to it. You can imagine with three-way factors as these gray circles here, you can actually change if you have them connected like this. That factor is connected to this node. So if this node turns to 0, all of a sudden it would disconnect these two elements of the graph. So now you have a flexible, changeable graph, which could be good for different kinds of environments that you'd like to watch, or it could be good for different computational routing strategies that you might like. So I think this is an important generalization that goes well beyond Gaussians and gives you a lot more expressive power. Okay, so that's the end of the microcircuit part of the inductive biases. And now I want to turn to just a couple other examples of inductive biases that we expect to see, but in less detail. We know that mostly in machine learning, we see feed-forward neural networks. Even the ones that are trying to be recurrent, mostly what they do is they just splay out time and treat that as a feed-forward input. Chris has a rare exception of a large recurrent network. The brain is highly recurrent. And that's a big macrocircuit difference between brains and AI. What does it do? What is it for? How does it help us? We have wide networks and narrow networks. Wide networks tend to be smoother, as I mentioned before, smoother functions, which can be a helpful or harmful regularity depending on what you're trying to do. Deep networks tend to be very symmetric. Every time that you add another layer, then any input that maps to the same neuron, to the same state of your layer, is treated the same downstream. And so you can think about this intuitively like origami or paper folding, where you're making maybe a paper snowflake. You fold and fold and fold, and then you cut a hole, and then you unfold it, and you get a complicated pattern, right? And that pattern is going to be duplicated with all that kind of shared structure here is coming down to a fairly simple structure when you, at the late layers of a deep network, after you've folded, every time you have a nonlinearity, you're folding your network in some way. And so you end up with a simple output giving rise to a complex shape. The deeper the network, the more intricate the transformations. Modularity. We've heard about modularity earlier today, and this seems to be another important inductive bias. Both Ruffin and Chris's architectures were both modular. And so that can give you a major inductive bias for reasons that we'll talk about in a little bit. Okay, that's all circuits. Then we also have learning. And the rules by which you learn will affect what you learn. So at the micro-learning level, we have synaptic plasticity. Synaptic plasticity in artificial neural networks is just backpropagation typically. I mean, that's the only one that really works at scale. Hebbian learning, very interesting, only learns one dimension, right? There's spike timing dependent plasticity has some compelling ideas. Nothing works at scale in machine learning. Backprop is the only one that does so. But if you look in biology, this is a simplification of a biological synapse. What's the learning rule, right? What's modulating this? It's a very complicated machine, and we are not including that level of complexity in our artificial neural networks. Is this all just for biological housekeeping? I don't think so. I mean, there's a lot of structure here that gives you many timescales, many dependencies. It can potentially solve some important problems. On the other hand, it's subject to certain constraints that artificial networks are not subject to. For example, locality, right? Your synaptic updates only can be with that one location that you have. You can only update based on the signals that are available to that neuron. That's micro-learning. Macro-learning is where you have a larger scale objective. So maybe you have a goal, maybe you're curious, right? If you have an intrinsic motivation of curiosity, that will change what you learn from the world. You can do active sensing that targets what data stream, it determines what data stream you have. And you can have a curriculum where we teach different things to babies and to college students because they're not ready for the same things at the same time. All macro learning bias. So that's the way that I like to think about the components of an inductive bias for these different artificial networks. And of course, they bleed into each other. So the right plasticity rule may depend on the microcircuit that you have, or the particular macro learning objective or intrinsic motivation that you have. So ultimately, we need to think about how these things interact. Okay, so that's how we can get, by having the right inductive bias, which is really a learning process from evolution, that's how we're able to go from being big to being small. And so this, I think, will have a lot of lessons that evolution has taught us that we can use in artificial networks. The other thing that has come up is constraints, right? And machines face different constraints than humans and other animals. Some pretty notable ones are time, space, energy, amount of data, right? There's some other that we might consider. How much memory do you have? How much computation can you do, et cetera. And so what is it that we do, our brains do, that allows us to lower our constraints, lower our resource costs, our internal costs, while still performing really well at many of the tasks that struggle with with 3 orders of magnitude less power, at least. So here I want to briefly go through this idea of having a reinforcement learning agent with representational costs. Most reinforcement learning agents are not using internal costs. They just focus on task costs. So you have your computational unit, which we can think of as your neurons. They influence the world through actions, which have some costs. And that changes the world with its own dynamics and gives us observations coming back to the neurons. And the neurons have their dynamics cost and their energy cost. And that's all on the implementation. So what happens to an agent when you start to consider those things? So in this case, we formalize it by a partially observable Markov decision process. Who here has heard of a PUMDP? Okay. Not everybody, but many of you. Okay, so the way that it works is we have a Markov world, which means that the changes to the world depend only on the current world state. There's your Markov transition probability. That gives rise to some observations with some probability. And you synthesize those observations over time to get a belief or posterior about the world using your Markov decision. There's a rule, hidden Markov model for this. So this is the probability of what you think is in the world now, given all that you've seen so far. And then to make it a decision process, we add actions. So here are your actions. The actions come in. You know what actions you took. That influences what you think is there. And you bounce back and forth between acting in the world and the world acting on you through your observations. That's a PUMDP. And you're ultimately trying to optimize some particular goal through your policy. Okay, so how do we optimize this? What's the objective? Usually it's it's a sum total of your expected future rewards, which is based on your state reward. Did you get to the juice or your points? And how much did it cost you to get there? So if it's a belief, if it's partially observable, then you can only make decisions on based on what you expect will happen. We can do that. And this is what people do in reinforcement learning. And now we are adding in these other costs here, a representation cost and a computation cost. Okay, this is not conventionally done. Mostly it's like, oh, you want a robot that performs really well? I don't care how hot it gets in its brain. So here we start by defining an unconstrained control problem, defining some internal costs, and then optimize for the combination, and then look at the interpretation of both. Okay, so in our case, we're going to take a very simple system because we want mathematical control over this. And so our goal is to control a partially observable world state. You want to stand at some place when the wind is buffeting you around, right? Balancing something while it's hard. But it's a partially observable world. So you get these partial observations and you have to integrate them to average out the noise. But inference is costly. So if you summarize your observations and have more information in your hidden internal state, it'll cost you. We're going to contrast constrained solutions that pay this internal cost, and we'll call them rational, versus ones that don't pay, they're unbounded. We can call those optimal. What I really mean is unbound optimal and bound optimal. So we're going to solve this in a linear problem. And this harkens way back to Kalman. And I'm just putting this up here in case any of you are reviewers saying like, hey, linear problems are not important. Like, yeah, linear problems have given us a lot of insight. First couple rounds of reviewers are like, we don't like linear problems. But Kalman figured out how to do inference in in these partially observable linear dynamical systems, and figured out how to do control regulation with the linear quadratic regulator. Top one's the Kalman filter. And then later they were combined into the linear quadratic Gaussian problem, which is what we're going to study here. So we have a state S, which is evolving over time. And here we're going to make it unstable, which requires you to exert some control. Yep. But you can exert some control through U, which is your control with an input gain B. And then there's some noise. So this is the dynamics of the world. We're in trouble here. And here are our observations about that world in the red dots. So now we estimate what the world is, accounting for memory, and we use that estimator to exert some control. And when we do so, that's not supposed to happen. Okay, now in order to solve this problem, we take all of the states that we just talked about above, we lump them into one big Z, a big vector, and then this whole dynamical system is describable by a single matrix equation, right? Single dynamics. And the only thing that all of this stuff depends on, at least in the limit of equilibrium, is this covariation between the state, the action, and your estimate. So if you know that matrix, you know everything. So we know that matrix, we can compute that matrix, which means that we can compute the costs of the rewards that we get from the state, the costs we spend to put us back balanced, and this is what we get when we control it. So instead of running away, our control allows us to keep things balanced. Not perfectly because there's noise. And now we add this extra cost in the upper right corner, which depends not on the action and not on the state, but on our estimate of it. This is your inference cost, right? This is different. So we have to minimize that total cost. And what that will do is it will change the way that we control the system. How does it change it? Well, if we didn't have the bound, we'd have one set of equations, which would be some control equation, u equals minus some control gain times your estimate. Here, it's a different gain times another estimate. And the estimate is going to be a little bit different because it's accounting for the costs. So it's the same form, but the bounded control is going to filter or integrate that evidence differently, suboptimally in particular. So this will give you a higher task cost, but a lower computational cost. So here, unbounded, you'd have this much cost, and usually you don't pay attention to the purple part, right? You're not worried about the cost of information. And so you're going to have this much task cost. But if you account for the costs, you're going to end up with a lower overall cost here. But you're going to move more. You're going to pay for it in some way, but the overall benefit outweighs the additional costs. And in this case, it actually, you get a better state reward, but you're working harder for it. Right, so you can see that this is a little bit higher than over here. All right. What happens is, depending on the parameters that you choose and how difficult the task is, you actually have a phase transition in when it's good to be optimal. There are some parameters where you just have to bite the bullet and do as well as possible, really do the optimal inference. And that's over here, when the volatility is high, and if you miss, you're going to fall over hard. But if you have a problem where it's maybe a little more forgiving, now you have a family of solutions, in this case, 2 different solutions, which we call skeptical and naive, which differ in how they weigh activity, weigh the different observations. And you go through different phase transitions, depending on what your penalty is, how much you pay for your internal thinking. So we end up with different dynamics. Here's a Roomba, like trying to vacuum up the dirt there. And you can see that they have different strategies, depending on whether they're skeptical and like not trusting the observation more than like trust it less than it should, or naive, believing every little observational fluctuation that it sees. Turns out that these 2 strategies are exactly the same in their total performance, but they have these different qualities. So you have an entire new family of bounded rational control, which differ in their particular strategies, but have the same performance. And this gives you a new free design subspace that, like, if you have a new task that you want to solve, then you can pick which one of these different family members you pick, which could give you a different performance. And you can look at this as a function of generalization. So here we're looking at the worst case scenario if you change the task. And in this case, the up is, I forget which one this is. This is higher is better. Label your axes, everybody. So in this case, let's see, the risk sensitivity, the average case, the skeptic, I think, is better. So I think lower is better. And in the worst case scenario, the skeptic ends up being worse off. But they generalize differently, right? As a function, as a consequence of their different strategy for meeting their internal costs. Okay, so in the last couple minutes, I want to return to the bitter lesson here. So you guys know The Bitter Lesson by Rich Sutton? It's so bitter. It's really sad. I mean, he's a guy who was very much inspired by biology. And what did he say? He said, we're trying to build all this knowledge into our agents, and this helps in the short term, but in the end, it's going to make a mess, and scaling is the only thing that wins. And I think that if that's really the case, then we don't need to look at the brain. But I just don't think that's correct. I think that there's a lot that we can learn from the brain. And so, you know, we're learning more. We're going to get this massive data. We really should be looking at these things. And so now, what is it that's going to help us do better? What is it that's going to help us generalize? Ultimately, it's parameter sharing, right? You have the same solution for different problems in some ways. Some elements of your solution for one problem transfer to another problem. And it's interesting to think about in the brain how you would do that, which is different than in an artificial network, where you can do things like copy weights, right? A convolutional network, you copy the weights. The brain can't copy weights. So how can we share parameters in the brain? How can we impose this kind of symmetry that would allow us to generalize better? And so here are three categories of ways where we can imagine this happening. The first one isn't really even a solution, but if you have statistics of the environment that are symmetric, and you have a developmentally encoded learning rule, like your plasticity rule, then you're going to learn approximately the same consequences of that plasticity rule for that data. So your learning rule will create a symmetry, approximate symmetry in your weights, approximate. If you want to have a symmetry where you do weight sharing over layers, well, that's easy. You can make it recurrent, right? A recurrent system is really just unfolded into a feed-forward system with the same weights. But maybe the most powerful here is over problems if you can reuse modules, which is why I think that all these discussions of modularity and routing are so important. I mean, arguably, we do that with our fovea. We look around and we dedicate our high-resolution hardware in our brain to different parts of the image without needing to copy all of that hardware for the entire visual field. Reasoning seems we have this ability to abstract, so we can take the same thinking process and apply it to different systems, whether you're talking about, you know, working in language A or language B, or variable X or variable Y. And probabilistic inference, I think, is an important one too. I think that probabilistic inference is a pervasive property of humans and many animals in some way. But the challenge that I have for thinking about whether this is a real inductive bias is, does that inference strategy transfer from one problem to another problem? Probabilistic inference is the right way to solve many problems, right? And so if you just have a lot of data and you learn how to solve that problem, you will come to probabilistic inference as your solution. But that's not an inductive bias. That's just the data talking. If you want an inductive bias, it means you need to be especially good at probabilistic reasoning or probabilistic inference. And then whatever that mechanism is, which is still deeply unknown, is something that we could somehow reuse, whether it's through modularity or recurrence or some microcircuit or a plasticity rule that's really good at finding those probabilistic elements. I don't know what it is, but that's the kind of thing that I think we need to look for in biology to transfer to machines. So we're moving towards an algorithmic symmetry. I like that symmetry back there. And so the messages are, yes, unlike Rich Sutton, some kind of computational structure should, I hope, improve generalization. And it may be better for the brain to model less of the world for paying less cost. So NeuroAI is a good opportunity, yay. Generalization is hard, computation is pricey, but brains have some good tricks. So let's learn from them. If you want to learn more about NeuroAI, we have a NeuroMatch class that was mentioned earlier by Guillaume, and check it out. And thanks to the people who did a lot of this work, and thanks to you for your attention.